Legacy modernization with AI agents, mainframe, ERP, and niche code. Modern enterprises often depend on decades-old software in languages like COBOL, mainframes, SAP ABAP, PLSQL, or VB6. These aging systems are hard to change and costly to maintain. Fortunately, new AI coding agents and design patterns now make it possible to incrementally modernize legacy stacks. In this article, we explore how AI-driven tools help parse and rewrite old code, and describe proven patterns, interface facades, the strangler approach, automated testing to replace legacy functionality gradually. We also cover data lineage, risk controls, rollback planning, and real-world ROI versus pitfalls. Even beginners can learn how to start. AI now unlocks coding by turning legacy code into understandable documentation or new code, so anyone can take the first step toward modernizing an old system. AI coding agents for legacy code. AI coding agents are tools that use machine learning, often large language models, to read, analyze, and even rewrite code. They can handle legacy languages no human on the team knows well. For example, Fujitsu's new Kozuchi AI tool can analyze COBOL programs and instantly generate human-readable design documents. IBM's Watson X Code Assistant for Z uses AI to convert COBOL functions into high-quality Java, guiding developers through each step. And Microsoft's open-source legacy modernization agents on GitHub uses Azure OpenAI and GitHub Copilot to parse COBOL and generate equivalent Java or .NET services. These agents capture business logic and data flows hidden in old code and help build new components around them. The key appeal of AI agents is that anyone can start using them. You don't need to write code by hand. Instead, you issue prompts or use specialized tools. For instance, a beginner could copy a small COBOL or VB6 routine into ChatGPT and ask for a plain English summary or pseudocode. The agent understands the code structure and can propose modern equivalents. This democratizes modernization. Non-experts can explore legacy logic without manual code reviews. Many vendors now bundle AI agents into accessible platforms. Capgemini's SAP modernization solution uses generative AI to auto-document ABAP code, halving effort on test scripts and conversions. The important caveat is human oversight. Agents speed things up, but developers still validate the output. In sum, AI coding agents accelerate discovery and mapping of legacy systems, cutting weeks of manual analysis down to days or minutes. Interface mapping, adapters, facades, and overlays. One challenge of modernization is mapping interfaces between new components and the legacy core. A common solution is an interface adapter or facade layer. For example, ERP systems often remain as the system of record, so new UIs or services must talk to them via clean APIs. An overlay architecture, or experience layer, sits between users and the old ERP. It translates modern calls into the old system's interface and vice versa. This adapter layer handles data mappings, authentication conversion, error handling, and buffering. For instance, it might map legacy field names to a new domain model, queue writes when the old system is slow, and standardize error codes. By isolating this code, you can rewrite or replace the ERP behind the facade later without changing the front end. This pattern ensures that you can roll out improved screens and services gradually, with the adapter translating between worlds. Another approach is to use an API gateway or facade as an entry point. AWS illustrates this in a strangler pattern for on-prem systems. They place an API gateway in front of the legacy app, then create new microservices behind it. All calls go through the same API facade, whether the request is still handled by the old monolith or by a newly deployed service. This maintains a consistent interface to customers while parts of the system strangle the old monolith. Over time, more endpoints are rerouted to new implementations. For example, only reading data from the old system initially, then later writing new data into the new service. In practice, interface mapping often combines these ideas. You deploy an adapter layer in front of the legacy system and expose a new API or web UI. New modules call the adapter instead of talking directly to legacy database tables or screens. This isolates old and new parts and makes it easier to redirect calls. If a new service isn't ready yet, the adapter proxies traffic back into the legacy code. If the new service fails, traffic can revert to the old system. More on rollback below. By building this shim, you can modernize one slice of functionality at a time without breaking everything. The strangler fig migration pattern. A related high-level pattern is the strangler fig approach to migration. Coined by Martin Fowler, it compares a vine that gradually grows around a tree and eventually replaces it. Rather than doing one big rewrite, you incrementally replace features of the old system with new ones. Early on, you add small enhancements as separate services that run alongside or on top of the legacy code. Over time, those new services absorb more and more business logic until the old system only handles exceptions. New functionality and even some old features are now in the new code, and the old monolith can finally be retired. Fowler outlines 4 steps for a strangler modernization. 1. Understand desired outcomes. 2. Break the problem into parts. 3. Deliver parts successfully. 4. Change organization to sustain it. In practice, this might mean identifying a key business capability, say order entry, rebuilding it in a new service, Node.js, .NET, etc., and then writing adapter code so calls for orders go into the new service instead of the legacy program. Because it's done in parts, risk is reduced. Each new piece can go live and deliver value immediately. For example, the AWS case study had an app that first handled only simple read-only queries through the new API facade, then later added write operations for a subset of users. At every step, the system kept working for users. AI coding agents help with strangler migrations by quickly creating or refactoring those new components. For instance, an agent can read legacy COBOL logic about calculating employee bonuses and generate an equivalent Java or Python function. You then deploy that as a service under the strangler pattern. A key to success is building transitional interfaces, code that exists only until migration is done. Many teams balk at extra waste code to connect old and new, but this transitional logic, routing, data syncing, etc., is what makes gradual migration feasible with lower risk. Automated test harness for legacy code. One lesson from failed migrations is that unrecognized errors can cripple a rewrite. To modernize safely, you need a comprehensive automated test harness around the legacy system. In practice, this means writing tests at multiple levels and integrating them into a build pipeline. Unit tests verify individual functions or modules. In legacy code, business logic may be hidden in large routines. Agents can help by suggesting unit tests. For example, asking an AI agent to propose input-output examples for a legacy function. Tools and frameworks, e.g. modern COBOL or PL/SQL test runners, can execute legacy code against these tests. Integration tests. Check that modules interact correctly. For instance, if your new overlay writes to an ERP database, an integration test ensures the end-to-end flow. Entry in UI to update an ERP still works. Agents may assist by auto-generating requests based on interpretation of interface definitions. End-to-end E2E tests simulate full user workflows. Before migration, you establish golden sequences of operations, log in, create an invoice, etc. Crawlers or frameworks like Cypress Playwright can automate GUI or API calls for those flows. This is crucial. It catches issues no unit test can. Regression tests, the safety net. Every time you refactor or cut over a feature, run your entire suite to ensure nothing else broke. Characterization tests, a classic legacy technique, are especially helpful. They record current outputs of legacy code for given inputs and assert that the new code matches that behavior. In other words, tests capture what the code actually does, so you don't need to know why it does it. Experts emphasize that regression testing is the most important layer. Before any change, make sure you have tests covering core functionality. Start by protecting mission-critical flows, orders, billing, approvals, anything directly tied to revenue or compliance. Then expand tests to fragile or high-change areas, modules with many past bugs. You don't need to do it all at once. Build your suite iteratively. For example, when a tester finds a bug, Write a new test around that scenario. Over months of consistent effort, even a skeleton suite can grow enough to catch major regressions. AI can automate aspects of testing too. For instance, AI test platforms, like some CI/CD tools, can generate intent-based end-to-end tests from natural language specifications. An agent can scan legacy code and documentation, then suggest test cases. In SAP Modernization, Capgemini's tools promise to automate test script generation with 40% effort reduction. And the native industry analysis found that writing tests still often takes 40 to 50% of a legacy project, but AI can cut that dramatically. Conceptually, you could feed a COBOL job log or legacy UI flow into an LLM to get a sample sequence of actions for testing. Regardless, the human must validate AI suggestions. The goal is confidence that new code matches old behavior before reintegration. Data lineage and risk controls. Legacy modernization isn't just about code. Data must move or stay consistent too. Data lineage means tracking where every data element came from and how it's transformed. Without clear lineage, it's almost impossible to ensure the migrated system is accurate and compliant. For example, when mainframe data, often in EBCDIC format, is moved to a modern platform, enterprises require forensic hash mapping and chain of custody processes. In practice, this means computing cryptographic hashes of data at each stage so you can prove it wasn't altered. It also means logging every ETL step. Every extract, transform, or load is auditable. Without this, auditors or regulators might not trust your new system. Data quality is a huge risk area. A modern guide warns that most failed legacy data migrations weren't due to technology, but due to dirty data copied straight over. Duplicate records, silent field drops, or inconsistent formats that crept into the old system can poison the new one, if not addressed. It's essential to perform data profiling and cleansing before migration. Not just rely on the ETL tool to move bytes. Teams should ask, have we identified duplicate customer records and decided how to merge them? Will every important field, even rarely used ones, map to the new schema? Is there a clear rollback plan if we later discover migration errors? Risk controls start with validating data at every step. Migrate in controlled batches. For instance, move history for 5 years of transactions first. Check reports for accuracy, then proceed with the rest. Use reconciliation scripts. After each batch, verify row counts and checksums match. If discrepancies appear, pause and clean data rather than forging ahead. Maintain a backup or transactional log of source data so you can revert any failed batch without rerunning the entire migration. In high-stakes cases, you might even run source and target in parallel for a while. Dual write, so all new updates go to both systems until the new one is fully confirmed. Essentially, build guardrails like you would in production, monitoring, alerts, and quick rollback triggers. Rollback strategies. Despite careful planning, migrations can encounter problems. A clear rollback strategy is non-negotiable to limit impact. The exact approach depends on your risk tolerance and downtime window. Here are common options. Fail-safe replication. Keep the old database in sync with the new system. For example, use change data capture, CDC, in both directions. After cutover, continue replicating from the new system back to the old. If things go wrong, you can instantly restart the old system with no lost writes. This is used in cloud migrations, e.g. AWS DMS, CockroachDB failback. Dual write or parallel run. Modify the application code or use integration middleware to write every transaction to both the legacy and new systems during a trial period. Then, if the new system fails, simply redirect clients back to the legacy environment. Dual write means no new data is lost on rollback, but it does double the write overhead and complexity. Manual cutover plus snapshot. For very low-risk cases, take a final snapshot of the legacy database. Switch users to the new system, and rely on manual data reconciliation if issues appear. This is only acceptable if you can tolerate some potential inconsistencies and have time to fix them. Feature flags, partial switchover. In a strangler approach, control what goes to new versus old via configuration. If a problem arises in a new component, you can toggle it off routing requests back to the legacy with no code rollback. This is like a very fine-grained rollback at the API level. Regardless of method, define rollback criteria and runbooks ahead of time. For example, if error rate spikes above X or critical data fails checks, initiate rollback steps. A recent review emphasizes matching rollback complexity to your needs. If zero data loss is critical, implement bidirectional replication or dual write. If some minor loss is tolerable, then manual fallback might suffice. Importantly, test your rollback procedures before the big cutover, so the team knows how to execute them under pressure. ROI of modernization. It's natural to worry about the cost of modernization. However, real-world cases show that the ROI can be very high. Legacy systems often consume 60 to 80% of an IT budget just for maintenance of old code. Compared to that ongoing drag, a one-time upgrade can pay back quickly. Industry analysis suggests AI-assisted modernization can cut project costs by around 70 to 80%. For instance, converting a 50,000-line app manually might cost $240,000. With AI tools, it could drop to $57,000, about a 76% reduction. That calculation includes labor, quality assurance, and tool fees. In practice, many firms report 5-year ROIs of 200 to 400%, often breaking even in 1 to 2 years. Concrete success stories abound. Deloitte describes a U.S. state that avoided a $200 million 10-year rewrite of a COBOL child support system by using automated refactoring into Java on the cloud. They completed it in 18 months instead, freeing budget for modern services. A Dutch insurer, NN Group, converted over 10 million COBOL lines to Java and cut IT platform costs by 80%, recouping investment in under 3 years. Even on smaller scales, AI helpers can accelerate discovery and coding. One benchmark cited a legacy migration going from 8 to 11 months down to about 2 months with agents, with labor costs falling by about $183,000 for a 50,000-line codebase. Of course, ROI depends on factors like continuing maintenance savings, reduced downtime, and the opportunity cost of new features. By automating the grunt work, AI agents free up skilled developers to build new products rather than babysit old systems. They also mitigate talent risk. Fewer firms need to scramble for COBOL or VB6 experts if AI can handle the legacy logic. All told, organizations find full-stack modernization more affordable and faster than ever, especially when done incrementally. Pitfalls and lessons learned. While AI and patterns bring advantages, there are cautionary points. First, AI hallucinations and errors are real. Generative tools can invent code or documentation that looks plausible but is incorrect. Fujitsu's solution addresses this by using a proprietary knowledge graph overlay that reduces hallucinations when generating design docs. Always validate AI output against known references or sample runs. Second, testing remains a bottleneck. Even if code conversion is fast, testing often still takes 40 to 50% of the schedule. Many teams underestimate this. You must devote time to robust CI pipelines and possibly AI-assisted test generation. Do not cut corners on test coverage. Legacy code is brittle by nature, and inadequate tests are a common cause of failure. Third, data issues often derail projects. As noted, technical migration success is meaningless if the data quality is poor. Failing to profile and cleanse data led many migrations to generate a new broken system. Invest in a data checklist, deduplicate, map every field, and include business stakeholders to define what clean data means. Build reconciliation reports before going live so you catch mistakes early. Fourth, scope creep and feature mismatch can surprise teams. Legacy systems often have hidden business logic and hacks embedded. Do not assume the old system's behavior is fully understood. Use characterization tests, as described earlier, to capture current behavior, and involve domain experts to explain unusual cases. When migrating UI or APIs, plan for the fallback, where the old interface remains until the new one is proven equivalent. Finally, people and process change matters. Patterns like the strangler require organizational buy-in. Teams must adopt new agile practices or team structures to let old and new coexist during transition. Getting business units to accept phased rollouts and testers to learn new tools is as important as the code. As Fowler notes, without cultural change, the new system could end up as muddled as the old one. Getting started. First steps. For readers eager to try AI modernization on their own, here's a practical way to begin. Inventory a small module. Pick a contained functionality, e.g. a single COBOL program, ABAP function group, or VB6 form. Gather its source code and any sample inputs. Let AI explain it. Use a tool like ChatGPT or an AI code assistant. Paste the code or key excerpts and ask for a summary or pseudocode. For example, explain the business logic of this COBOL code. The agent will highlight loops, calculations, and data usage in plain language. This bridges human understanding with the legacy syntax. Generate a test or doc. Prompt the agent to produce a test case for that code, or ask it to output a diagram or API schema of what that module does. You may get an initial unit test or design doc for free. Build a harness. Even a simple script that calls the old code with test inputs and checks outputs establishes a baseline. If the agent provided outputs, verify they match the actual program. This check also trains you to spot AI errors. Decide how this functionality will live in the new architecture. Will it become a REST microservice, a cloud function? Sketch the data contracts. You can ask the agent, convert this legacy output into JSON fields. Use a sample migration tool. For example, Microsoft's legacy modernization agents repo includes demo agents for COBOL. Or try a trial of a tool like Phoenix Code, which supports Delphi, Power Builder, VB6, etc., to see automated conversions for your language. Involve your team. Share the AI outputs with colleagues or business analysts. Validate with a domain expert. Is this translation correct? Keep iterating. The first next step is simply experimentation. Pick a non-critical piece of legacy code and run it through an AI tool. Play with prompts until you get a meaningful conversion or explanation. This low-stakes experiment gives insight into both the promise and quirks of these agents. From there, you can expand to a formal strangler phase. Define the first feature to strangle and write the adapter code needed. Conclusion. Modernizing legacy systems no longer means reading 40-year-old COBOL by Flashlight or hiring scarce experts. AI coding agents and smart architecture patterns have opened the door for even novices to make progress. By using incremental methods, API facades overlays, and strangler migration, building strong automated tests, including characterization tests, and planning data validation and rollback, organizations can transform old stacks safely. The ROI can be dramatic, as studies show costs halving or more. The key is to stay disciplined, validate AI outputs, involve business users to define correctness, and don't skip the plumbing like tests and logging. Start small, iterate, and learn from each slice you modernize. With these tools and practices, that 30-year-old system can evolve into something nimble and future-ready, and the next person up can link your new modernized system together with confidence. All links to sources are available in the text version of this article. You can find the full article at easycoding.tools/blog. Thanks for listening. For more practical AI coding guides, tool comparisons, and resources for builders, visit easycoding.tools. And if it's easier to remember, just go to aibuilds.it. It redirects to easycoding.tools.